Welcome back, folks. We're going to look at a bit of a strange way to go find values in a circuit. And it ends up not being very practical to target a value in a circuit and then go find it. We'll do that only because it helps us practice the technique over and over again. Rather than having that as the goal, the real usefulness of this technique is that we can reduce the complexity of the circuit that we're analyzing. So maybe we can reduce the number of meshes, or we can reduce the number of nodes, and make our analysis fit within the capabilities of our calculator or the back of the napkin we're working with. We can make things simpler, but there are some implications to it. In order to do that, we're going to use Thevenin's theorem and Norton's theorem, and we're going to switch back and forth between them. Okay, so we're going to call this source conversions. We take a voltage supply with a series resistance and we convert it to a current supply with a parallel resistance, or vice versa. All right, so to start us out, we're going to get a blank sheet of paper here. We're not going to solve one like this yet, but there's my notes. Crap. Let's keep going, because this is already take two. I don't like doing multiple takes. Blank sheet of paper, go! There we go. Hey, it worked that time. All of my lecture notes that I'm looking at while I'm talking to you, that I usually have printed out in front of me in the classroom. So in order to start this, we have to get comfortable with the idea of taking a Thevenin equivalent circuit. Okay, so let's start by drawing that. So here's our Thevenin equivalent circuit. Okay, it has some resistance R Thevenin. It has some voltage V Thevenin. And we want to find the Norton equivalent of the Thevenin equivalent circuit. This is going to get a little circuitous. It's a good thing that that's what we're analyzing here. Okay, so find the Norton equivalent. And I'm going to do this without numbers for now. We're going to have plenty of time to look at problems with numbers, but we want some formulas out of this because we want to be able to do these conversions pretty quickly without having to think. As is always my goal, how to solve problems without thinking, or thinking just the right amount, right? So if I want to find the Norton equivalent, the first thing I do is short where the load would be connected and find the short circuit current. Okay, and since that's a short, now we know the voltage across R Thevenin, and we can say I short circuit is equal to V Thevenin over R Thevenin. It's that simple. It follows Ohm's law too, right? Volts over ohms is going to give me amps. So that's always helped me remember it. Maybe it'll help you remember it too. So we found I short circuit, which of course is equal to I Norton. Okay. We want to take that same circuit and we want to find R Thevenin. So let me do it here. Let me scooch my chair. Okay, so we're going to find our Thevenin, or we're going to find our Norton, excuse me, by replacing the independent supplies. I'm going to use method 1 here, first method I introduced, and we're going to look back into it from here. Well, there's only one resistor, and we're connecting to it on either side, so we can say that R Norton in this case is simply equal to R Thevenin. Okay, and that's it. So we can take that knowledge and we can come up here to this circuit, right, our original Thevenin equivalent circuit, and we can convert it. And we can redraw that circuit as a Norton equivalent. Okay, current's going to go up. In terms of Thevenin equivalent values, now this is R Thevenin, and this is going to be V Thevenin over R Thevenin. Okay, so that's the first conversion. We go from a Thevenin to a Norton. Now we got to make sure it's a Thevenin, but if we know that it's a Thevenin, we can disconnect this circuit, redraw it this way, and then connect it back at the same two nodes. Okay, so that's our first conversion. So that one's good to kind of put away in your head. Now all we got to do is do it backwards. Okay. So let's get a nice wall here, and let's do the opposite. So let's start with a Norton equivalent that looks like this. Okay, we're going to connect our load out here. We've got R Norton, we've got I Norton, and we want to convert to a Thevenin equivalent. Circuit. All right, in order to do that, we're going to find V open circuit, which of course is V Thevenin. And the load is not drawn here, so we're going to find V open circuit here. Well, look at this. There's only one current flowing in this circuit, and we can say that V open circuit is I Norton times R Norton. Okay, so again, following Ohm's law. And that's, of course, V Thevenin, right? Okay. Now let's go find R Thevenin. So we play the same game. We copy the circuit. We replace the independent supplies with their ideal resistances. This one's just going to be an open, right? So now you've got these wires hanging out here to nowhere. Since they're not connecting anything and I'm not interested in any values around them, we can come back here and say, well, we're going to find R Thevenin just by looking into the circuit there. So if R Norton is equal to R Thevenin, you would certainly hope that R Thevenin is equal to R Norton, right? So R Thevenin is equal to R Norton. So using that knowledge, we can draw the Thevenin equivalent of our Norton equivalent circuit. This all sounds crazy, right? Like, how are we going to solve problems with this? We're going to solve problems with this. Good times will be had. Some people latch onto this technique, and they're just like, I love doing source conversions. I'm going to try to solve every problem using source conversions. And I totally don't recommend that. Okay. But if you like it, it's kind of fun to puzzle through everything. Let's see. So that voltage supply is I Norton, R Norton, and then the resistance up here is R Norton. So there's our second conversion. So using these two conversions, we're going to try to simplify circuits. We're going to simplify them all the way down to find whatever value we want. But like I said, it's a little more practical to use this method to remove a mesh or maybe remove a node or two, so that you TI-36 folks that can only solve 3x3 systems, this could really help you, especially if you're on the FE exam with that particular calculator or some other calculator that has a similar limitation. Okay, so keep these conversions in mind, keep the image up as we move into the next video. But what I'm going to do is I'm going to draw a circuit, and then we're going to start making conversions. And as we make conversions, we'll combine things and we'll reduce it down as far as we possibly can. My goal, at least while I'm teaching this topic, is to make everything an Ohm's law problem. We'll see if I can pull that off. Okay, so examples coming at you next. Stay tuned and good luck.